Guys, hope you're doing fine, and sorry for the delay in making this video, but please check out my poll on my channel because not many of you have voted yet. So coming back to the question, as you can see here, it is like a number theory question, and what it says is you have to determine all positive integers k such that the equation a squared plus k is equal to b squared has no solutions in integers a and b. So in other words, you can write this as k such that k belongs to z plus, which is positive integers, and S is a set of tuples a and b, and these tuples are such that a and b are integers, and a squared plus k is equal to b squared. Now this part is important. So the set S here, which is this set basically, is a null set, meaning there are no possible tuples a comma b. So what we have to do is determine all positive integers k such that this set S over here is a null set. Let's see what we can do. So here's a solution. So if you go back, this was the equation we had. A squared plus k is equal to b squared. So what we're going to do is just transpose a squared here and express k as the difference of two squares and use the identity. So that's what we're going to do. Transpose a squared to the right and factorize using the identity. What we have to do is, like I said, express k as the product of the factors, which are the factors here. In our case, it'll be b minus a because we're working with b squared minus a squared. Remember, we transposed a squared to the right. And this was plus a squared here on the left side. So to avoid integer solutions, k should be strictly expressed as a product of two numbers such that when equating the two numbers with the factors on the right, we get two equations which result in a unique solution of non-integers. So basically, we are going to express k as the product of two factors, basically, or divisors. And then we're going to equate them with one factor with a plus b and the other factor with a minus b. And then we'll get two equations here, and then you can just add up the equations or subtract the equations, and then you'll get the values of a and b. And now we have to do something to make sure that a and b are not integers. Let's see what we can do. So this means k can't be expressed as a product of two integers with same parity. So basically, parity is the property of being either odd or even. Basically, it is like you have to figure out whether it is odd or even, and then that'll probably help you solve the question. So basically, suppose you have two divisors of k, basically two factors of k, a factor pair of k rather, such that both of them are odd or both of them are even, like mentioned here. Then what would you have? You would have two odd numbers multiplying to a plus b and a minus b. So one odd number is a plus b, the other odd number is a minus b. So if you add up the equations, odd number plus odd number, you have an even number. And here also you have 2a. So you'll have a possible solution for a, and same goes with b. Odd number minus odd number, so you have an even number. And b minus negative b gives you 2b, so you'll have solutions for that. And the same thing applies for even numbers. But what if we make one odd and one even? But there's a catch. Let's see what that is. So one factor of k should be odd as discussed. If one is odd and one is even, we can tackle this. And the other should be even in such a way that no rearrangement of k's prime factors results in any two factors with same parity. That means this should be such an even number such that you cannot rearrange these factors in such a way that one is odd and one is even, or one is even and one is odd, or sorry, one is even and the other is even, which we don't want. So basically, if this is a multiple of 4 or this is a multiple of 4, you can rearrange the 2's. There are two 2's in 4, right? It's 2 times 2, so you can just send 1 2 here, and then it's still balanced, but both of them are even right now, and the parity is satisfied. So even if this was once an odd number, you can just rearrange the factors and make it an even number, and then you'll have solutions. So what does that mean? That means the maximum power of 2 is lesser than 4. That means the maximum power of 2 in case prime factorization is 2 power 1, which is 2. That means this implies the even number should be the product of 2 and an odd number. And here the even number refers to the even divisor. Okay, so now let's conclude the answer. So we have k is equal to 2r plus 1, an odd number, into an even number times an odd number. I mean 2 times an odd number, because we don't want too many 2's to allow rearrangements. And here we're taking r as a positive integer. So if you expand this, you have k is equal to 8r squared plus 8r plus 2. Now, here comes a more interesting number theory part. Now, we're going to solve the equation modulo 4. So basically, we're going to divide each thing by 4 and take the remainder. And then we're going to express it as 4 times a natural number plus the remainder. And that'll give you k, right? Because we're going to do the quotient times the divisor here plus the remainder. And that'll give you the number itself, the dividend. So here you have 8r squared is congruent to 0 mod 4. That is the mathematical way of saying it. So basically what that means is 8 leaves a remainder of 0 when divided by 4. And same goes here, because no matter what r is, it's a natural number, so that won't really hurt things. It'll still be divisible by 8. Same goes here. So this is also divisible by 4, so the remainder is 0. And all we're left with is 2. So therefore k is congruent to 2 mod 4, meaning k leaves a remainder of 2 when divided by 4. So therefore, the answer will be k is equal to 4n plus 2, where n is a natural number here. So basically, any number in the form 4n plus 2, where n is a natural number, will not satisfy the equation at the start. This one. So what we can conclude here is that any integer, any positive integer in the form of 4n plus 2 satisfies this kind of equation for avoiding integer solutions. So you can try it for yourself. For example, let's take a simple number like that. Let's take 6. Can you find any two perfect squares which when you add 6 to one of them, you get the other? You'll definitely not find one. So basically, we can now conclude it using this kind of proof also, like substituting numbers. So basically, we're safe. Our answer was correct. Take any number in this form. You'll find that you can't find any two perfect squares which, when you add one to the other, you get the other square. Or the difference of two perfect squares can never be 4n plus 2. So that's it for today. Hope you enjoyed my video. Thanks for watching. Hope you enjoyed it. And hit the like if you really did. Subscribe for more videos. Goodbye. Thank you.